Hi, welcome to the next video section in this synthesis course by Cubase Guru. As you can see, the next section is called Sound Sources, and the first section of the sound source part of the course is regarding basic wave shape. Basically, what this is going to be is an overview of the kind of 5 most common wave shapes that you should be able to find in any synth, or most synths anyway. That'll be your sine wave, your sawtooth, your square, your pulse, and your triangle waves. I'm going to give you a certain level of explanation regarding these waves, but I'm not going to go too deep into things like the maths of the harmonics and stuff like that. That can be something, if you're really interested in that you can go and look up elsewhere. I'll give you an overview of how it works, but to get right into that stuff means that this course would have to get to a different technical level where I really don't want to take the course to that level, really. Okay, so without further ado, let's get on to the first wave, which is the sine wave. Now, we all know what a sine wave looks like. We've seen it a couple of times in this course. I can again show you. So here we have, I've got Zebra installed, got the Blue Cat oscilloscope here, and the sine wave looks like this. There you go, there's your sine wave. From here all the way around to there, if I can just... From here to there, so from there to there is one complete cycle. The higher the frequency, the shorter the cycle, or the more cycles per second. So for instance, if I do a really low note, as you can see it's a very wide waveform. And as I come up the keyboard by octave, you'll see it getting the waveform getting closer and closer. As you can see, so there you have it, your sine wave. Okay, a little bit about a sine wave. Here we have the basic spectrum. Here we've got the relative level, so 1 is 1 decibel, and we've gone out as far as the first 10 harmonics. Now a sine wave only has one harmonic, which is known as the fundamental, or the first. The sine wave is also the simplest waveform out of all the waveforms, which makes it unsuitable for subtractive synthesis, simply because there's no harmonics to be filtered, and subtractive synthesis is based on being able to use a filter to subtract harmonics from the original source sound to create a new sound. So being that the sine wave has only one harmonic, as shown here, it's no good for subtractive synthesis because there's nothing to filter out. Basically, if you were to turn the filter down, you wouldn't hear anything. So that's our sine wave. Next wave we're looking at is a triangle wave. Now, the triangle wave is very, very similar to a sine wave, apart from obviously a few differences. The triangle wave itself's got 2 linear slopes that you can see here. Again, there's the full cycle. However, the difference between the triangle wave and the sine wave is that the triangle wave has a small amount of harmonics. Not much, but enough so that it can be used in subtractive synthesis. There is something that can be filtered out. So again, looking at the same diagram here, the first harmonic in the spectrum is the fundamental, as you can see here. Now, being that the triangle wave has a little amount of harmonics, you can see them here. You'll get one on the 3rd, the 5th, the 7th. The one on the 3rd is 1/9 the first harmonic, so 1/9 is prominent, I guess, is the best word to use. The 5th one is 1/25th, and the 7th one is 1/49th, and so on, and so that would be 181 or 181st. Now, this is the kind of stuff that I'm not going to get into too deeply. As you can notice, there's a mathematical relationship between these numbers. For instance, the 3rd harmonic is 3 times 3, which is 9. The 5th is 5 times 5, which is 25. The 7th is 7 sevens, which is 49. The 9s would be 9 9, which is 81. Now, again, I'm not going to get into these mathematical relationships. All I really want you to know is that a triangle wave is similar to a sine wave. However, it does have a small amount of harmonics, which means it can be used in subtractive synthesis. And if we go back, I can show you triangle wave, and let you hear it. As you can hear, it's very similar to the sine wave, although you can hear the overtones of those extra harmonics. Sine wave, triangle wave. So, as you can see, they're very similar as well, apart from the sine waves being kind of rounded off at the peaks there. But they sound quite similar as well. Okay, the next wave I want to talk to you about is the square wave. Now, as you can see, it starts up there, down there, down there, up there and up there. You can't really see the red there, but it's there, believe me. Okay, things that are unique to the square wave. It is odd harmonics only, which you can see here. So we've got again our first fundamental, but then 1 on 3, 1 on 5, 1 on 7, 1 on 9, there would be 1 on 11, 13, 15, 17, so on and so forth. As you can see, the third harmonic is 1/3 as prominent as the first harmonic, then 1/5, 1/7, 1/9 respectively. Because of that, your square wave gives a kind of hollow feel, or a hollow sound to it. You'll often find square wave used in things like organs, organ type sounds, and basses as well. A lot of really deep hollow basses, you'll find the square wave in there. And the square wave itself has a very synthetic feel to it. Again, we can come back in, I can let you hear a square wave. So again, it sounds quite hollow. But there you go, there's your perfect square wave there. The next wave is our sawtooth. And as you can see, there's your wave, one cycle. And you can see why it's called a sawtooth, because this section here looks like the teeth on a saw. Now the sawtooth's unique. Well, it's not unique because things like pulse waves and stuff can have both odd and even harmonics, but it always has odd and even harmonics, which makes it very bright, and because of that it's brilliant for subtractive synthesis. This is the starting waveform for most sound designers when working in subtractive synthesis, because it's got so many harmonics, and you can see the harmonic relationship here. It's just great for filtering out. As you can see again, you've got your fundamental, then your second harmonic is half, third is a third of the fundamental, fourth, so as you can see it works its way down. So you can see your saw wave pattern there really. So our saw wave for those of you who are into psychedelic trance, the favourite saw wave of the psytrance bass line. For those of you who aren't, you'll find a saw wave is used a lot in synthesizing sounds, especially in the subtractive area, because it's so bright. There you have your sawtooth. The last waveform I'd like to talk about is the pulse wave. As you can see here, it comes up here, then it's shorter, then wider and up. Now, your pulse wave, your square wave is pretty much a pulse wave with equal dimensions, so equal width on each side, or the pulse wave is central, I guess. Now, a few things about your pulse wave. The harmonics are dependent on the ratio between the two parts, the ratio being the width here. As you can see, the ratio is small there, large there, so the harmonics are dependent on this ratio here. That ratio is known as several different things. Mark space ratio, which you probably haven't heard of before. Shape, maybe. Duty cycle or symmetry. More often than not it's symmetry, because it's the word symmetry goes very well with the way it looks. And again, in perfect symmetry, i.e. this section here only being this wide, and then coming up there and this section only being this wide, that's your square wave. Because of the nature of the wave, it can contain both odd and even harmonics, which again makes it very bright. However, the overall harmonic content increases as the pulse width narrows. So again, great tool for subtractive synthesis, and you can get a whole host of sounds coming out of this. One of the great things to use when doing sound design with a pulse wave is to have an LFO controlling the pulse width modulation. Pulse width modulation basically means modulating the size of the pulse. So you'd have an LFO making this wider and shorter, depending on what it was that you were after. Now let's have a listen to the pulse wave. Now it's a bit different to show this in Zebra, and I thought the easiest way to do it would be to show you, and by the way, I forgot to mention it first, this is Zebra 2.5, but I am using the unempty Dark Horse skin. Sorry, I should have mentioned that at the beginning, because it does look very different with the 2.5 skin. I prefer this one. But anyway, now the way I'm going to show you the pulse operating in Zebra is, but if you come here and click More OS 1, because I'm using the pulse table, down here we've actually got a square wave. So there's the square wave, which actually sounds better than the square wave. Oh, it's actually the same. So yeah, we've got the square wave here, as you can see here. But what we're going to do is run up through the different waves, and that shows you the pulse. Yeah, as you can see, the pulse is getting thinner. And you'll be able to watch that happening here, and you'll listen to what happens to the harmonics. Eventually, it completely disappears. So square wave, there's a nice pulse. As you can see the pulse here. Thin at the top, thick at the bottom. So that's your pulse wave. And as you can hear, there's lots of harmonics in there that can be filtered. So that's it for your basic wave shapes. I hope this has given you a more fundamental understanding of why certain waves may be used for certain sounds. Now, like for instance, you may be saying to yourself, well, what am I really going to use a sine wave for? Well, let's just do a little experiment, shall we? Just to give you an idea. I'm not going to do this with all of them, but let's use this saw wave here. And let's create, let's say, just a little offline bass pattern, we'll call it. We'll just do this. Now this is just one reason why you may use a sine wave. Okay, so we have that saw wave there, but it's okay. But what we could then do is duplicate that part and use the sine wave. Now, obviously what I would do is just add another oscillator here with a sine wave on it, but I'm just going to show you it like this. So now what I've done is added the sine wave on the same note. So if I just solo that, okay, add them both together, and what you're doing is reinforcing the bass on the saw wave. That's one use for sine waves. Other uses for sine waves will come in later parts of the course, things like additive synthesis. That's the 5 basic waves. You'll notice I've not put noise in there. We'll get to noise at a later part of the course, but that's your 5 basic waves, waveforms. I hope that's helped you out, and I'll see you in the upcoming videos.